This is Dr. Kavita Singh, Associate Professor in Department of Civil Engineering in Institute of Aeronautical Engineering. So today we are going to discuss a topic called as map projections. So till now, if you remember, we have discussed about raster data, vector data, spatial data, non-spatial data, what are the different types of input methods, how we use in GIS, what are the different types of data we use, what is non-spatial data. That all we have discussed in the previous lecture. Now after we input this all kind of information in GIS, finally whatever output we need to project it through the map projection. So map projection is like projecting the image, fitting the image, the real world information from 3D to 2D without changing its any properties. That is called as map projection. So let us start with this topic today. So our contents will be today for this map projection. Map projections, basic concepts and properties of map, projection, area, shape, distance, direction, classification of map projection. So what is map projection? So the term map projection can be thought of literally a projection. That means literally a projection means projecting one image to a, so let us say this is 3D real world, okay, 3D real world data. So if you want to project on a 2D, so this data is transferred from 3D to 2D is called as projection. So for example, if we switch on a light placed inside a translucent globe. Translucent globe means suppose there is a globe here. So if we switch on a light bulb placed inside the translucent globe. So suppose there is a bulb here, bulb in the globe. So if you switch on this, so whatever projection on the globe which is appeared on the surface of the globe will be projected on the wall. Okay, will be projected on the wall. So this is called as projection. So globe, the images, translucent globe, the images on the surface of the globe will be projected outward. So that is called as a map projection. So whatever features which is on the 3D, whichever it is on the globe, that is transferred to the wall is called as map projection. So this globe is 3D and the wall is 2D. So automatically this data is transferred to the wall. So without changing of the properties, without changing of the area and distance and all, if we are able to transform the information from 3D to 2D is called as map projection. Now for example, this is one example of map projection. So this is a globe, right? This is a globe. Now here you have a torch. We have switch on the torch. So if this torch is falling on this globe, now what is happening, whatever information which is on the globe, it is projected on the wall. Okay, so this is 3D and this is 2D. So this is how the map projection looks like. So when a projected image hit a wall, we have map projection. Okay, when a projected image hit a wall is called as map projection. That means 3D information when it hits to the wall and it converts to 2D is called as map projection. So map projection is not done using the analog method. Instead, cartographers use mathematical formula to create the projection. So cartographers, who are the cartographers? Who creates the map. So creating of the map is, they are called as cartographer, and this cartographers will be creating the map, and that with the help of the mathematical formula. So therefore map projections can be defined simply as a mathematical transformation. So simply as a mathematical transformation of locations is called as map projection. So mathematical transformation, it's not like simply converting this 3D to 2D, whereas the totally mathematical transformation, okay, is called as map projection. So in 3-dimensional space of Earth surface on 2-dimensional space of map sheet, we can transfer the information with the help of the mathematical transformation is called as map projection. Now we have here map projection in GIS. So we have different ways of projecting the information, the map transformation. So if you see here very clearly, we have this globe here, right? globe, this is also globe, and this is also globe. So these three globes are projected differently. Now if you see this, observe this, this is like a cylinder. So cylinder means if we cover this total globe with a paper or a cylinder, or fix a cylinder on it, and later we cut from one side, so how it will be projected? Like this. So this is the cylinder if we cut from one side, so it will be projected like this, or else like this. So this is called as cylindrical projection. So this projection is like 3D. The cylinder is 3D. Now while cutting this from a between, it will convert to 2D. So this is called as map projection. Okay, map projection. Now here you have a conical projection. Okay, conical projection. So what does the conical projection do? Now here you see there is a globe here. This is 3D globe. 3D globe. So on this globe you have a conical kind of 3D paper or something, like if we keep a model here, and then if you cut this from the center or a side, and then if you laid open, then this type of conical projection will be displayed. Conical projection will be displayed. Now if you see here, we have a azimuth projection. So azimuth projection is like this is the globe. So over the globe you have this paper, if you keep this 2D map, and then if you cut this map simply to the flat surface, so this is 3D, completely flat. So this is called as azimuth. Okay, so these are the different types of the ways of projecting the 3D image to 2D image. 3D image is like the real world data is called as 3D, and the information which is mathematically transformed to the 2D is called as projection. Now basic concepts, properties of map projection. So what is the main concept of map projection? How we call it as a map projection? So here we have an example of an orange, right? So if we squash an orange on a flat surface, for example, this is orange, okay? So if you flatten it, so what will happen? So it will spread like this, something like this, it will spread, okay? So after flattening, it will lose its properties. So once it is flattened, the properties are lose its properties. So the skin of the orange will split and spread out in all the directions, and original properties of the orange, such as its shape, will change. Shape will change. It will change like this. Okay. So this is your orange. It will change like this. Okay. So this is not the correct way of projecting. So similar change properties will occur when try to project features on Earth's surface onto a piece of paper. So similar thing will occur when we try to project features on Earth's surface to a piece of a paper. Okay, so this is how the example I was telling you about. Suppose this is a Earth surface 3D. Okay, so once you flattened it, or let us say orange. Okay, once you flattened it, so this is how it appears. Once you flattened it, this is how it appears. So what happens after flattening? It loses its properties. Okay, loses its properties. So the idea of projection is like, without losing the property of the Earth surface while flattening, while converting to 3D to 2D, the properties should not be okay, loosed. So you have to just take care that properties should remain same, should not be lost. Okay, so converting 3D to 2D is like, while transformation, there should not be anything happen, that mathematical property should remain same, and the property should not be lost. Some of the properties of the spherical Earth will be lost, and as a result, the areas and shape of the features as they appear on the paper will be changed. Now, and distance and directions between the individual features can no longer be maintained after the projection. So whatever distances, when the properties are lost, properties of flattened surface are lost, then what happens? The directions between the individual feature no longer be maintained after the projection. This is what happens once the Earth surface is flattened. The spherical Earth will be losing its property. So spherical Earth will be lost, and as a result, the shapes and the direction and the individual features no longer it will maintain after the projection. Now, therefore, whole idea of map projection is about preserving the properties of real world features when they are depicted on the map. So, therefore, whole idea of map projection is about preserving the properties. So, preserving the properties is like from 3D to 2D when you are converting, 2D when you are converting, preserve. So, while converting, preserving the properties is of real world feature and they are depicted on the map. So these properties include the following. So what does the properties include? Area, shape, distance and direction. So these are the different properties which to be maintained while transferring from 3D to 2D. Okay. Now area, a map projection may be designed to be a equal area so that area measured on Earth. Such a map projection is called as equal area or equivalent projection. So area means the projection may be designed to maintain its area, so equal area, so that any area which is measured on the Earth surface such as map projection is called as equal area or equivalent projection. So the equal area property can be fulfilled or distorting the shape of graticule. So graticule, a network of lines representing meridians and parallels on which a map or a plan can be represented. So this property shows the sizes of the real world features to be visually compared on the same area basis. Now next if we talk about shape. So a map projection can maintain the correct shape of the spatial features on maps. So shape is converting, for example, here is your Earth surface. So this is your Earth surface. So on the Earth surface, so for example, you have a water body here. This is your water body. So this water body, the shape should be maintained while transferring. When you are transferring to the 2D, the same shape should be maintained like this. So while transformation, the correct shape of the spatial features on the map. Okay, so this property is accomplished by making the scale along the meridian and the parallel the same in the both the directions. Right. Next is distance. So preservation of the distance can be achieved only by selecting certain lines along the scale remains true. So distance is like about the, let us say about the roads. When you talk about roads, when you're transferring, transformation is from the real world. For example, this is the road and it should be transformed to the 2D. So if you are transferring, it should transfer the same. Okay. So there should not be any of the property lost. Exactly how many kilometers it is here. Same should be transferred here in the kilometers. For example, it is 10 kilometers. So exactly 10 kilometers should be transferred in the 2D from 3D to 2D. Right. This is what the certain lines along with the scale remains the true. So the line of the true scale include the central meridians of the cylindrical classes of projection as well as the standard parallels of the conic class of the projections. Now distance preserving map projections are called as equidistant. So whatever preservation is taken care here is that type of projections are called as equidistance. So while equal area, here we have equidistance. So preservation of area is called as equal area. Preservation of distance is called as equidistance projection, which is transfer from 3D to 2D. Okay. Direction. If direction measurement made on the map are the same, direction measurements made on the map are the same as those made on the ground. So if the direction are same, like for this is the 3D map. So this direction, if it is north direction, here we have south direction. So whatever direction west, east, so same direction should be transformed in the 2D. Okay, so same direction should be here it should be north, here it should be south, west and east. So same direction should be transferred for the real world 3D map to the 2D. So the projection is called as true direction map projection. So here we call it as true direction map projection. We have equal area, we have equidistance, now we have equal. True direction map projection is called as map projection. Now classification of map projections. So we have area, shape, we have distance, we have direction. Okay. Now we have a classification of map projections. So map projections according to the type, developable surface on which the network of meridians and parallels are projected. So networks of meridian and parallels is projected is like a developable surface is surface that can be laid out flat without the distortion. So what is the classification of map projections? In the previous slide also I told you, like converting the information from exactly from the 3D to the 2D information, and it is laid on out or the without on the flat surface, flat surface without any distortion. Okay, there is no distortion. It is laid down on the flat surface directly. Okay, so there are three types of developable surface which are called as map projection: cylindrical, conical, and planar. So we have three types. Planar is also known as azimuth projection. Okay. Now let us see in detail. So three main types here: cylindrical, conical, azimuthal, or planar we say. So cylindrical is this. In the previous slide also I told you how it will be. So it will be covered like a cylinder from all the sides, and we cut open from one side, and it will be laid down like a flat surface. Okay, so this is how the projected area, this map total globe will be projected in the cylindrical projection. Okay, cylindrical projection. Later if you see conical projection, so the cone is kept on the globe. So if you cut open from the center, it will be like a fan shape. That is called as conical. Now here azimuthal means you just flatten this entire globe. Flatten the entire globe. So this type of projection we call as planar or azimuth. Okay. Now see, cylindrical projection is assumed to be circumscribed or transparent globe so that the cylinder touches the equator throughout its circumference. Now assume that a light bulb is at the center of the globe so that the graticule of the globe is projected on the cylinder. So by cutting open the cylinder along the meridian and unfolding it, that's what I was telling you. So this is your globe. Okay, this is your globe. Now you have a cylinder here like this. Cylinder means if you keep a paper like this, if you wrap the paper on the globe and then you cut from the center, okay, from along the meridian. Along the meridian means where you have a 0 degrees. Along the meridian, if you cut open and unfold it, then you will be finding the cylindrical projection. So a rectangular cylindrical projection is obtained. So the meridians are vertical and parallel straight lines intersecting the equator, right angles, and dividing it into 360 equal parts. So the parallel will be horizontal straight line at some selected distance from equator and from each other. Now this is how it is represented. So here you have 0 degrees. Okay. So here from the center, if you cut, it will divide into 2. So from here center it is cut. Now it is divided into 2 central meridians: 0, 20, 40, 60, 80, 100, 120, 140, 160, 160, 180. Okay, like this till here also you will be finding 20, 60, you have 80, 100, 120 till 180. From here 0 degree from 180 here, 0 degree from 180 here. So this is how when you cut open this cylinder, it will be like a rectangular surface and it will be 2D projection. 2D projection, and this is 3D. Okay. Conical projection. So a cone is placed over a globe in such a way that the apex of the cone exactly over the polar axis. So this is the cone. Okay, this is the cone. So here you have a globe. Here you have a globe. This is the globe. So exactly this apex is on the top. So if you cut open from the center and then display. Okay, cut open and then display. So exactly over the polar axis, the cone must touch the globe along a parallel latitude known as the standard parallel, which can be selected by the cartographers. So along a parallel latitude known as the standard parallel, which can be selected by the cartographers. So along the standard parallel, the scale is correct and distortion is least. So if you see when the cone is cut open, along the meridian and laid flat, so that was like this is the cone. We just keep it on the globe. So from here, from the center, cut open on the center and just laid flat. So then what happens? This will be like, the projection will be like this. Okay, projection will be like this. Here you have 0 degrees, like this. Right? You have a projection in this like fan shaped manner. Here you have the meridian. From prime meridian you have like this, latitudes and longitudes. You have a projection like this. Okay, 0 degrees, 20, 40, 60, 80, like this till 180. Till 180 you have, and from here also 20, 40, 60, 80, like this till 180 degrees you have the projection like this. So this projection is called as conical projection. So when the cone is kept on the globe and it is just cut flat, when the cone is cut open along the meridian and laid flat, so that kind of projection will be conical projection, and without changing the properties of the globe or properties of the real world, that becomes transformed to a plane area or transferred to a 2D map called as conical projection. So a fan shaped map is produced. So this is the fan shaped. Okay, fan shaped map is produced with meridians as straight lines radiating from vertex to equal angle. So it will be radiating from vertex to equal angle. So from here, straight line, okay, like this. Okay, so this is called as conical. This is what I was telling you about. So this is your globe. This is your cone. Okay, so here you have 0 degrees. So it is just kept on the globe. Now later what we are going to do is, we'll just cut it from here. So once you cut from the center, so this is what the cut is. Once you cut from the center, like fan-like shape, okay, fan-like shape will be displayed like this. Okay, so here you have 0, 20, 40, 60, 80, 100, 120, 140, 160, 180. So till 180 you have, right? So if you see here, 20 degrees, 40 degrees, 60 degrees, 80 degrees, 100 degrees, 120 degrees, 140 degrees, 160 degrees, 180 degrees. Okay, so this is east, 180 degrees east. Now here 180 degrees west. Okay, east, west. Now here also you have 20 degrees, 40 degrees, 60, 80, 100. You have 100 here, 120, 140, 160, 180. So till 180 degree here, 180 degree here. So here is the prime meridian. Okay, prime meridian. From here 180 degrees east, here 180 degrees west. Now you have your north, south. So this is how the projection will be projected in the conical projection. Okay. Now planar or azimuth projection. So planar, it is known as planar and azimuth also. So a plan is placed so that it touches the globe at the north or south pole. So a plan is placed so that it touches the globe at north and south pole. So this is the your projection here. This is the earth. Now if you keep a plan on this center, okay, here you have north, here you have south, here you have east, west. So this is your actual real world. Okay, Now if you real world, if you keep a paper on this and then you flattened it, so it will give the flattened, this will conceive when the cone becoming increasingly flattened until its vertex reaches the limit of 180 degrees. So its vertex should reach till 180 degrees, okay, like this. Then it will be, so the projection resulting is better known as polar or azimuthal projection. So as straight lines radiating from center at the circle, which is the pole, so these meridians projected as straight lines radiating from the center of the circle. So center of the circle here is the pole. Here is your azimuth, okay. So here you have pole, okay, North Pole. So this is flattened now. So this is radiating like this from all the directions. Or on this you have the map like this. Okay. So these meridians are spaced at their true angles. The parallels are complete circle centered at the pole. Now this is how it looks like. Azimuth or planar, if you talk about, it's like this is the pole. This is the pole. Now from pole you can see radiating from all the sides. Okay. From here you can see. So 0, 20, 40 degrees, 20 degrees, 60 degrees. You have here 80 degrees, 100, 120, 140, 160, 180, right? So here again you have 160, 140, 120, 100, 80, 60 degrees and 40 degrees and 20 degrees. Here 0. So 0 is your prime meridian. Okay. So this is how the azimuth and the planar projection looks like. So if you see from here 0 degrees, it will go like this. Again it will complete here. So this kind of projection you have, and the parallels complete circle centered at the pole. So this is how the parallels will complete the circle at the center of the pole, and the straight lines radiating from the center of the circle will be, which is the pole, is called as azimuth and the planar projection. Okay, so this kind of if you remember in the olden days, this kind of projections are used for just navigating purpose. Okay, so these projections are usually used in the previous days. Nowadays we are using the cylindrical projection. So most of the map, if we see, it is in the cylindrical projection, because the converting the whole information to the 2D map is called as cylindrical projection. So I hope today's lecture we have learned about different kinds of projections. So what is map projection basically? So map projection is basically transforming the information, the exact information from 3D to 2D without losing its properties. Okay, without losing its properties. So once you flattened it, the properties should remain same. So it's a mathematical transformation from 3D to 2D information. So that is called as map projection. So here we have seen the basic concepts are like concept should be, area should be same, distance should be same, or direction should be same, measurement should be same. So these all things we have to consider while transformation. So here we have different types of projections, that is the cylindrical, conical and the azimuth. So these three types of projections. So basic idea of converting the projection is converting the exact information from the real world to the map, because that location should match in the map system. So that's how the projection will look like. Then only the accuracy will be made. So this is about the map projection. These are the different types, and these are the few references you can go through for finding out the more content about it, you can go through the Anji Reddy book. And online contents you can just go through for finding out the more content. Tangcheng GS TMH publication also you can just go through for the map projections and all. So that's all for today's lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.